Yeah, so thanks, Ryan, for the introduction and for having me. It's really a pleasure to be here. And it's the first time I think that I've talked again in person. Real audience. Good. So what I will talk about is what I call universal neural simulation based on inference. I think an indie code is called physics and astrophysics. Or something like that. I will give you mostly examples from astrophysics. Right, so let's get started. Good. So you know all about astroparticle physics is, I think, just for some motivation. So astroparticle physicists care about like the largest, connecting to the largest and smallest scales and learning something from looking at the universe at large about particle physics and for using their particle physics knowledge to learn something about the physics in the universe. So an exciting research field. And one of the big questions that falls into that research field is what's actually dark matter made of. Astronomers, of course, see dark matter in many observations, but particle physicists tend to ask what's actually the particle properties of dark matter, how was it produced, what else happening, and so on and so forth. 83% or so of the mass in the universe is dark matter, so it's kind of a serious problem. And there have been many proposals for what dark matter could be, ranging from primordial black holes all the way to ultralight matter. So I think there are like 80 or so orders, at least 80 orders of magnitude mass uncertainty concerning the dark matter part. Good. So how can one progress? Well, all the models that are still on the market, of course, agree with observations of the universe at large. So if one wants to make progress, one has to look at details. Details like gravitational wave and different models affect different of these detailed observations. One has to look, for instance, one can look at gravitational waves and maybe hope that dark matter halos around compact objects affect these waveforms. Another example would be, for instance, gamma rays, where the annihilation of weakly interactive massive particles in the galactic center could cause like extra emission in gamma rays that we could observe. Another example is, for instance, stellar streams, which are disrupted as star clusters that circulate around the Milky Way halo, and they are affected or can be affected by dark matter substructure, for instance, as predicted by coordinate matter model. So these are just a few examples. There are dozens of data sets that we can look at, where we have to look for very tiny deviations from the models that we know. I understand better for astrophysical objects, for astrophysical conditions, and see that matter affects it. And so the goal is to look for small deviations and anomalies, precision observations on astrophysical objects. Good. So one problem is here that there are two problems with this. So one is in the future, the amount of data that we will have to analyze will just increase more and more. Talking about thousands of petabytes, which can be blamed on SKA, but also many other experiments that are not radio experiments will actually collect large amounts of data process. We call it a quantity problem, but data also becomes typically more detailed and more accurate. For instance, if you look at the galactic center, right, in the past, these maps here look extraordinarily noisy, so you could get around with very simple models actually trying to understand the emission history. But for instance, Fermi, we have now pretty high resolution maps with high statistics, so the models that we actually have to describe the data start to fail. Same for instance, stellar streams and many other data sets. So we have to keep up with the quality of the data by making the models more complex, more realistic, more detailed, and actually find ways to compare them. So that's the big question. How can we keep up efficiently? And that brings me to one of the key problems. So one is, of course, thinking about better simulations, making them accurate, maybe faster, maybe more detailed. The other is then how to actually then learn from data, right? How to go back from a specific set of observations and learn about the underlying physical parameters. I'm visualizing this here. So typically the situation, as physicists, what we know more or less how to do is we start with physical parameters, a specific model, then we have either analytical or numerical approaches to make predictions for the data, right? So we know this forward path. can be very hard. That's kind of our business. But then going back is actually hard as well. So once you have, sometimes physics tells you the probability of observed data given the model, right? But then what we're actually interested in is the probability of the physics model given observed data. And you have all heard about like frequentist approach to this problem and like Bayesian approach. I will focus here entirely on Bayesian statistics. So yeah, solving this problem in the framework of Bayesian statistics is just boiling, in some sense, just boiling down to using Bayes theorem, right? And this is just basically the law of conditional probabilities. Very simple. The ingredients, you will all know them. I just repeat them here. One is like a likelihood or a simulator. That's kind of the forward model. Given your parameter Z and your physical model Z, we kind of have usually a way to estimate probability of an observation X, or at least simulate possible observation X, which is like drawing from probability X. And we typically can or have to, in the Bayesian framework, we have to specify priors, so your prior knowledge or prior belief parameters of interest, your prior likelihood or probability for your theory. And then posterior is just given by like multiplying. It's very simple, right? And dividing by Bayesian X, which is a normalizing factor. Make sure that Pz with X is normalized. So that by itself looks very simple. The problem is then that in reality, the number of parameters, for one of the problems is that in reality, the number of parameters can be very large. So for anything between 1 and billions of parameters. And the traditional ways, or some of the traditional ways how to deal with getting the handle on this posterior, so for instance, that's the sampling technique, don't scale well with the number of parameters. Already, if you have like hundreds of parameters, you typically would require to evaluate this quantity here. I think here 1 billion of times. So that's a very large number of times. But what I show up here is actually something that I should explain. So this here is basically the likelihood function here, Px in Z. Often we are in a situation where we are interested in a few parameters Z, maybe one parameter Z, let's say the dark matter mass. But then our model also has a very large number of nuisance parameters, which I call the eta, which we really don't care about. They just happen to be the parameters that describe all the details of observations. But we are not interested in. The problem is to get to the posterior for our one parameter of interest, we have to do this often really large integral over all the nuisance parameters, which can be dozens or hundreds or thousands or millions. And that process is usually or often solved by simply drawing initially samples from the high-dimensional posterior. So instead of looking directly at the one-dimensional posterior, we try to first get samples from the million-dimensional posterior, and then just project it onto the one posterior that we are. So that's typically like the classical likelihood-based inference. I will talk a bit more about this. And now, thanks to modern developments, basically neural networks, thanks to the ability to train neural networks, there has been a new class of algorithms called simulation inference that actually make it possible to look at this problem in a completely different way, solve problems that have been possible to solve. So just to give you some idea, real-world data is pretty high dimensional. So just look at these like 5 images that I just randomly downloaded from unsplash.com, I think. If you think about these are just random images, right? If you think about how many parameters you would need to parameterize random images, I mean, you could do the number of pixels, right? But then you also you actually wouldn't parameterize anything. You would just have a noise generator essentially. So you need something with semantic meaning, and then like okay, there's a ship. The ship has like this number of windows here, blah blah blah, this color. So these are maybe thousands, maybe millions of parameters. These are a lot of parameters that you could, in principle, like dream of writing a generated model for images like this, which you then parameterize, right? And then integrate it. And doing this like explicitly by integrating over all possible images would be among this task, right? But you can easily use your brain to kind of do this integration. integration, without actually integration, and just look at this example here. So these are like 9 mock data images, so to speak, and just look at the image and the parameter next to it, right? So this is 1, 8, 3, 4, 9, 8, 1, 2, 4, 3. When you see this last image, you will not have hard time to predict or to guess what number corresponds to this image, right? Look at this, it's probably 8 or 9, right? It will not be 1 or 2. And you just had, I mean, you just required like 9 training examples, right? That's really a low number of training examples. Basically, what you just did is you trained your neural net observations to map effectively observations of parameters. Working pretty well. And the reason is that you recognize, your brain starts to recognize patterns in these images rather than just trying to compare images with the observed data. The problem with comparison is the following. So let's imagine this here is an image, right? Then you have to say, this here closer, or is this here closer, right? This here the moon in the right position, this here has the background right, but the moon in the wrong position. So comparison is context dependent. If you look at training data, a few examples, you will realize we care about this kind of similarity, not about this kind of similarity. But typically, if you do likelihood-based approaches, what you actually would get as a result, none of them is similar, right? Because usually in a likelihood, in the easiest cases, you would try to get each and every pixel right. So typical likelihood from an image analysis problem is something like this, where this is just like pixel noise, sigma, and then you try to compare the flux in each pixel or the value of each pixel with the prediction pixel. But in a likelihood-based approach, you really want to get the image right. And there's no way around it because otherwise the likelihood. And so the effect is typically that likelihood-based approaches require a very, very large number of examples. You need a subset of examples which happen to look similar to your data pattern for the data. It basically boils down that to the fact that the algorithms, likelihood-based algorithms, are blind to how the images actually look like. They only care about this, like distance measure, which isn't very targeted. Well, I will give more concrete examples. Good. So what does this mean practically? Well, just to give you an overview, so this here is a diagram like model complexity in the direction, and like realistic models for astrophysical data often have really large number of parameters. And this here is the number of simulations, or the quality of simulations. So if you have high quality simulations, you can't run many, so you will typically be here up in the parameter space. If you have low quality simulations or fast simulations or surrogate models, you can run many. And then you can use these traditional algorithms like so what neural, what simulation-based inference really helps you is to handle models with a large number of parameters, complex models where you maybe can't run that many simulations because you want the complex simulations that they take time. Right? We'll give you some examples. What I want to talk about and focus now is the one specific algorithm that we proposed. We call this truncated marginal neural ratio estimation, which falls into this class of neural simulation-based inference algorithms. And it has a bunch of properties that we found desirable, which other algorithms have, but they don't have them all at the same time. So the algorithm that we proposed, which we also accepted Europe, one of the major machine learning conferences. So our algorithm can do targeted inference simulation efficient and also locally amortized. And it gives you as answer basically the same thing that you would get from MCMC samples. So directly, everything works well, you get posteriors, complicated posteriors. Good. So as I said, the algorithm falls into this class of simulation-based inference algorithms. That's a very active field of research. We can look at this paper by Kai Kramer and collaborators, where it's 2009. But they categorize different simulation-based inference algorithms. So generally, the logic of these inference algorithms is to approximate posterior. So it's very similar to what we heard in the last talk. Some variation inference is one version also of this. kind of separate. I will talk about. But the general idea is instead of sampling from a posterior, you try to approximate it. You can either try to approximate directly the posterior, or you can have algorithms that approximate the likelihood, which you then can use to get the posterior. Or algorithms are also out there, and ours is one of them, which are actually approximate ratios like this here. So this is the ratio between probability of data and parameters divided by the margin. That will give you some idea about this. You can use all these quantities to like work them towards the theory. Good. Just to give you again something. So what do these quantities here actually mean? So P of Z was our prior, right? And P of X was our Bayesian evidence. So let's suppose our model is like generating cat and donkey images. Then our prior would be basically drawing labels, either cat or donkey labels, like binary. And Bayesian evidence, if we would draw from the Bayesian evidence, we would randomly get either the cat or donkey images. If we draw from this joint model, then we would get labeled cat or donkey images. Okay, so we get an image and we get a label and they match, like in this example. However, what we also could do is we could draw first an image and then a label individually, and then that's called marginally, because we draw from the margin. And then what we get is just random labels with random images, which sometimes match and sometimes don't. Okay, so that's something that we can do, right? And that we can easily do once we have the simulator. So you can, for basically all kind of problems, you typically have a simulator that, given the parameters, simulates your possible observation, right? So you have to define prior. So whatever problem you have typically something that generates your random parameter point from the priors, and then something that generates your random sample from the simulator that corresponds. And then you do this 1,000 times, you get 1,000 examples that are like jointly drawn, and then you scramble randomly, reshuffle labels, relations, and you get examples. Good. So how does this happen? Well, what we know, where does neural networks? Well, the trick is now the following, and that's sometimes called the likelihood relation. Imagine we now train a neural network, not a neural network to predict the parameters, but we train a neural network to predict whether the image label pair was drawn marginally or jointly. So our neural network would take as input these XZ pairs and would output the number between 0 and 1. And the number would be the probability that either H0 is true, which is drawing jointly, or H1 is true, which is drawing marginally. Okay, that's something that you can train a neural network to. That's just binary classification. Good. And yeah, I wrote it here. So we train a neural network that outputs probabilities between 0 and 1. And if it's 1, then the parameters match. So you will have a cat image with a cat label, H1, and they don't match, and that would be shown. Good. So how to train this? Well, it's as I said, it's a very straightforward machine learning task. You, for instance, can use the primary cross-entropy loss function. Let me explain. So that's just the loss function as function of the network, which I called T. So T has a lot of parameters called I here. These are all the millions of network parameters. And then the loss function is simply this integral here over the joint probability distribution times the log of the network plus the marginal probability distributions times the log of minus the network. Okay. Of course, we can't actually do this integral, right? That's possible. It's complicated. But what we can do is then we can minimize this loss function with stochastic gradient descent, just randomly providing samples either from this or from this example, and running this and basically approximating the loss function by dimensions. And what one can then show analytically by just taking like the function derivative of the loss function with respect to E, with respect to all the network weights, is that the thing that minimizes this loss function happens to be this ratio. So here's jointly drawn divided by jointly drawn plus marginally drawn. And you can easily see that if you just now divide this thing by px times pz, right, this becomes 1, and this here becomes the ratio that I wanted to approximate. So once we have the network, we have this quantity. Okay. And I didn't write it here. So px comma z actually is like px given z times pz. So you can cancel the pz. Then you get a likeness by evidence ratio. Or you can do this the other way around, and then this here actually equals the posterior divided by the prior. Okay, so the only thing after training the network that you still have to do is multiply that thing by the prior. Then you're done. So network structures can look like this, for instance, just to give you some ideas. So one would have, for instance, here some data input and some parameter input. And the way we did this in practice usually is we use kind of pre-processing network. If you have image data, it's typically convolutional neural net or something like that, which compresses maybe our like 1000-dimensional data into like, let's say 10 feature vectors, 10 feature parameters. And then they are just thrown together with the rest of the parameters that you're interested in into a dense neural net. And this is then the thing that we train. So under the hood, this behaves a lot like approximate Bayesian computation, where this part here, I don't know if you know that, but those of you know. So this part here would be kind of the kernel density estimation. This here would be the feature, the thing that learns the test statistic, the summary statistic. And training the neural network gives you simultaneously an estimate for the optimal summary statistics, as well as the posterior. That's pretty efficient. And what's interesting with this is we can now instead. So let's say we are interested. We have like 100 parameters in the model, but we are just interested in one. Okay, then the way we get directly to this one-dimensional posterior is simply to only feed the one parameter of interest in this neural network. And then the entire thing will automatically learn the marginal posterior for the one parameter we care about. Perfectly marginalized over all the rest. And so that's kind of the logic. So in the CMC run, you would have to do sample from the full joint distribution with all kinds of correlations, where you get all kinds of correlations with all kinds of parameters. The simulation-based inference, you can directly just get this answer, forget the rest, which is great because then the rest can be rather complicated. So you basically directly jump to the conclusions. The difference is simply in the likelihood-based approach. Getting rid of nuisance parameters would require integration. The simulation-based approach is getting rid of nuisance parameters just means you ignore them when you train your network. That's it. Yes?
In that procedure, so when you are identifying the parameter you want to marginalize, are you adding any kind of bias in your? Say at the end is that you have many parameters, right? Whereas we care most about setting boundaries in one of the parameters or identifying this one. Are you kind of biasing things toward that parameter so that you have done the full of it? We get a different answer or
no, asymptotically, it's a question. Asymptotically, on paper, you have a flexible enough network and a very large amount of training data you get. It's asymptotic against the same. And yeah, that's the answer. The level sits in the formally exactly the same. Right. So another nice thing is now, let's say we are actually interested in two parameters and their correlations, or another parameters and two parameters and their correlations, right? Then we can just simultaneously train all kinds of density estimators just for the one-dimensional margin. So we could train an estimator for this parameter, and then for this like two-dimensional correlation. So this all can happen simultaneously, and we would learn like optimal summary set of optimal summary statistics that works well for whatever question we have. So just to show you an example, which also is our Nurex paper. what this example here shows is something that is pretty hard to do with, let's say, so let's look at this posteriors, right? So we have like two modes in each direction. So if you just look at two parameters, we have 4 modes. But then we look at 10 parameters, which gives us 2 to the power of 10 modes, which is around 1,000. Or we can look at 20 parameters, which would be like 1 million modes. Running an MCMC algorithm would in principle require to like touch all modes, right? You want to have at least maybe 1,000 samples from each mode, otherwise you might not trust your answers. If you do the same thing with the algorithm that we propose or other similar algorithms, you actually can directly get the answer with a pretty low number of simulations, typically thousands enough. So the number of simulations is far smaller than the number of modes that you would have in the full problem, but it's far larger than the number of modes that you have in the problem that you're actually interested in, which is enough. So here in this case, we would be actually just interested in the 1-dimensional and 2-dimensional marginal posteriors, which have. And you see that our algorithm does well compared to other algorithms. So this here, for instance, would happen if instead of trying to train just the marginals, it's probably trying to train the joints. Then you see that it's very hard to pick up all the structures correctly. It's good to directly jump to the marginal posteriors that you have. Because you are simply solving a simpler problem, right? So that's you get the same answer. So another aspect of our algorithm is now the following. So what the algorithm actually learns is you feed in all kinds of observations with all kinds of parameters. It doesn't only learn one posterior, as I show here, but it in some sense learns all of them. Okay, so it's like an inference machine afterwards. You train the network, afterwards you can throw in any observation and you instantaneously more or less get the posterior without rerunning anything. That's quite useful, and for instance, using gravitational wave astronomy as one of the proposed methods to get very fast information about where the signal actually comes from, right? So that's quite useful, but it can be also quite wasteful if you have very, very tiny regions in the parameter space, very concentrated, small, very focused posteriors. Then you want to have like a method like with MCMC that zooms into the relevant parameter range and generates more simulation where it actually happens. There are quite a few techniques that were proposed in the context of simulation-based inference. These are so-called sequential methods, which kind of start to simulate more in regions which are close to the posterior. We propose a new method called truncation, which is compatible with this idea of marginalizing multi-parameter. And this is simply based on the following observations. If you have an integral over nuisance parameters, right, over let's say full real number space, then you still get the same answer if you focus your integration regime onto a small subset, where the posterior is not zero. So you can, in practice, this looks like the following. So let's say this here is your initial prior. This is the posterior. Then in several rounds, we will estimate how the posterior looks like. You can see this here. Initially, the estimate will be quite poor. We will pick up all the structure. But you can use it to exclude parameter space. And then we find a new prior, which is more focused on the region we are interested in. Train there a new network, gets a better approximation to the posterior, and iterate until we converge. So that's our kind of version of zooming into the relevant parameters. It's just a comparison with previous algorithms, so ours doesn't do worse on test data sets, comparable. Good, but what I wanted to talk about, what time do I have? How much time? Okay. I have to stay 15. Okay, so one thing that is interesting is now, this was one of the reasons to think about this truncation scheme. Once you train the neural network, right? So let's say we have a very complicated observation, we have a very complex model. How do we actually ever start trusting the answers that the neural network gives us for some posteriors, right? So that's that's tricky. If you have like standard inference algorithms, you have some intuition for when it fails, when it works, how long you have to run your CMC sampler, and so on. For neural network, it remains a black box. So what to do? Well, one of the huge advantages with neural networks that you actually don't have with MCMC is that you can test them, right? So you can't simply plug in other data and see how they behave, right? You can plug in all simulated data and see what answers. You couldn't do this with MCMC. With MCMC, there's a difference, like test data set, you run the MCMC, you don't want to do this at all. But with a neural net, once it's trained, you actually can do this test. Like you can do tests like, hey, how often does actually my like 1 or 2 sigma region, how often does it include the true value, right? That's a question that one can ask. In the Bayesian context, there's something that one could define called effective Bayesian coverage. I think this term comes from this pretty recent paper by May from Yamas and collaborators. So the basic idea is, let's imagine this here is our like highest probability. So this is the 68% probability region, highest probability. Just to visualize it. So that would be these typically corner plots. This would be the like densest region, the most preferred region. We can then ask, okay, how often is the true value, which we of course have to know for our test data set, how often is it actually included in that region, right? Visualizing this here, so the regions are green, 1 sigma, and red, 2 sigma, and the true value is red. So you can just throw in a lot of examples and just count how often the red line intersects either with the green or the red. So that's something that one can do, and one can do this actually not only for like 1 sigma and 2 sigma and 3 sigma, but also everything in between. And then just make these kind of plots here, where you see actually, hey, my 1 sigma region contains, so this is for some random example from the paper here. So you see, okay, or you see that our 68.3% credible interval actually contains the value in 70% of the case. So that's a good thing, right? And our 95% interval in 96%. And even our 99.7 interval in 99.8% of the cases. That's great, right? Because it's a confirmation that this thing actually gives you believable credible interval. One interesting observation, that leads for ratio estimation, that typically if you start training the network, it gives you like conservative answers. So it wouldn't be overconfident. You wouldn't start excluding randomly things that you don't want to exclude. If you kind of asymptote from above. That's not a general statement, that's a statement for this particular example, but yeah, whenever you have a trained network, you can actually see whether this works, right? That's useful. And if it doesn't work, you can even like readjust your interval. Say, hey, I actually plotted the 60%. Good, let me give some concrete examples. Well, one is cosmic microwave background, which kind of is a bit absurd because all the studies of the cosmic microwave background are based on the Planck likelihoods nowadays, and that's like we know the likelihood, right? There's no ambiguity. The likelihood is given. So why should one do like simulation-based inference in that case? I would explain. So what we did is we basically Alex told. So he took some of the simulators for Planck data, so in this case, and massaged it into something that generates simulated Planck data rather than for TP, E. And then what we can do is we can just see how many samples we need to get the full answer that you would otherwise have to. With 1,000 examples, we get this year. With 2,000 examples, we get this year. And with 5,000 examples, we get here the red contours. What is shown in MCMC, what is shown in red are the MCMC results, which here require 100,000 simulations. So a factor of 20 more. And you see that if you try MCMC with just 1,000 samples or 2,000, it's a bit like cheating in the sense that, of course, you can smooth this to also look nice in some sense. But this year are the Swift results, TM and RE results without it. And so we can get results with far less simulations, even on problems where likely. What is more, so for generating this plot here, which includes 13 Nuxus parameters, The CMC sampler actually had to care about these multi-nuisance parameters, whereas with TMNRE, we basically just ignore them. So they are not, they just don't appear when making these plots. So this posterior, for instance, this neural network that generated this posterior only has ever saw the baryon density. And this year has only ever saw the product meta density. This year has only ever saw product meta baryon density. And still you get the same result. Yeah.
So agree on these three correlations for each of them.
Yeah, so each of them is, all of them are based on the same embedding network. But then for each of them, this is a relatively small dense network with 2 layers and a bunch of parameters.
So this basically, what you do in CMC, you is just one, right?
Yeah.
But in this case, you have many parameters up to train many networks.
Yes, but
end of the day,
you can do this at the same. So we kind of try to solve the problem where simulations are expensive, training stuff on GPU is cheap. I mean, that's kind of the assumption, which kind of is true. So doing this here actually requires like 30 minutes or something like that. It's not a massive amount on a GPU. The reason is that you can train this here in parallel. So you can just plug them, all the networks next to each other and do this in one go. This, of course, doesn't scale if you have like a million of these things, right? If you want to make a corner plot for 1,000 parameters, it starts to become not that much fun. But for this year, good. And just an example for the truncation scheme. So if you have a wide priors to start with, then the code will zoom into the parameter. So what you see is simply visualized training data. So initially training data is used over a large region, parameter space, and then in subsequent rounds, it's kind of more focused on the relevant region. And this makes the posteriors better. So initially the posteriors look like the bluish regions, at the end they look like. And kind of convergence checks are as usual, you just increase the number of samples by factors of 2 until the result doesn't change. So that's too much different from what you do in the case of good, and then we can also do these coverage tests, right? So for each of these posteriors, we can just check, hey, is this actually working out very quickly? But this would be impossible. How much? 6 minutes. Okay. So another example, strong length. That's ongoing work since kind of 2 years and started actually or motivated all this. I can just give you very briefly the idea. So, because CMV data is pretty simple, it's just a spectrum, right? So, but this year is very fast. So what's the idea? Well, we have strong lensing image, strong lensing consistence. We have the lens galaxy and the background galaxy, the red one, and the dark matter halo of the lens can deflect the light from the source galaxy and Einstein rings or multiple images. So far, so good. That's what you see. It depends then very much on the matter content of that galaxy. What's so interesting is if there is like a little subhalo, just a little amount of little subhalo, a little field halo along the line of sight, this will perturb that part of the image, in addition to the main perturbation that you got already from the lens. And what this will do is it will affect this part of it. So you see here the same galaxies several times, right? So you have several times the same image. What this perturber will do, it will just affect one of these images, one of these projections. And so you can use this in principle doing product. Just as an example, so this here is just two times the same background galaxy. That's by dark matter halo. That's a little actually pretty large perturber here. It will affect the image in the way that you see there, and affect in particular the reconstructed source down here where it will not affect the one. That's just an illustration. It's not like how to do to show you that these are two times the same galaxy, but this here would be the reconstructed background galaxy. Here would be affected. So what's the problem? Well, in reality, okay, of course, we could not just train a network, right? On this. So we have a network that generates lots of these images. We train it. The network learns how much to tell us how much substructure. The problem is the images look all very different. So these are just 100 or so 60 lenses from HST. They all look completely different. And the effects we're looking for are like are the percent or sub-percent. So perturbations from subfields would be indistinguishable high. Training a neural net on images that are so different and at the same time look like percentile effect is really hard for nobody has done this. There are examples in the literature where people do this kind of simple twice analysis, but this here is really complex because each galaxy looks different. So the way we want to solve this problem, right? Observation, we want to work backwards to some dark matter. Just sorry for jumping back. What's interesting is, for instance, in the case of dark matter, that depending on the temperature of dark matter, so this is warm dark matter, cold dark matter, the amount of substructure can be different. So measuring the presence or non-presence of these perturbers can tell you something important about whether cold dark matter is true or not. Right? So good. So how did we approach this? I have 3 minutes left. Then it could get like 20 hours talk. But there's basically a 2-step process. So instead of training a neural network on all possible problems, we first kind of zoom into the problem and determine in some sense priors which are relevant for the problem at hand. So we don't do this with the algorithm that I just described, but with some variation. With variation inference. So we heard about this in the last talk. So the idea is to maximize the elbow. I'm not going too much into this. So basically, in some sense, a fitting problem. Or in our case, like 100,000 parameters, and to actually fit it in some sense in Gaussian process. We describe the background galaxies by effective Gaussian process. And you can see that starting with this image here, we can get a good fit. So this is the residuals. This here is the true source. This is the reconstructed source. For these mock images, this is the funny looking galaxies. So you see, we can reconstruct them pretty well. Thanks to variation inference, I can say more about this if you want. And then we use this variation posterior, which is like now a posterior for 100,000 parameters, to generate training data which already looks pretty much like the image we are interested in. So the training data for the neural net, which then does this ratio estimation that I was talking about before, simply looks like the image plus some perturbations in the source, plus some perturbations in the mainland, plus like all kinds of variations of where the subfield is. And then we train the network to give us one single answer, which is like, where actually is the cutoff in the subfield mass function? So is there a cutoff, or are there subfields below a certain mass? And this works. It doesn't. You see that the posterior doesn't look very strange, which is due to the fact that there are only a few subfields in the end in each image, so there's a lot of subfield noise, if you want to say. But if one starts combining many images, actually one can get good constraints. This is still at the conceptual level up to now, so there are all kinds of challenges to make this work. Real data, it works pretty well on mock data. I can tell you more about the challenges if you want. But that's the plan. So basically, setting up a pipeline where we first, maybe basically multiple steps, start generating training data for neural nets that looks closer and closer to a given observation, and then solve the integration problem. There are other examples. I have 1 minute left, so I want to talk about Swift. So this is kind of the outcome of much of our work. The truncated marginal neural ratio we wrote to Swift, which is supposed to make this easy, and we use it for what we are doing. So this was used for CMB example and used for netting example. It does what I was describing. So you can specify the margin that you're interested in. You can have coverage tests, into the relevant parameter space. You still have to define your own neural nets. So that's something that's very data dependent. So if you use this, you end up writing neural nets, CNNs, whatnot. But kind of the statistics part and the commonalities between all these analysis problems are so good. And just some last slides where I want to kind of give you some general idea of where this plays a role. Just make it what earlier this one. So it's similar to the one that I already showed. So imagine a plane. Look at this plane here. So there's the number of parameters again, which ranges like from 1 to 10 to the 8. this direction, and then this is now the number of simulations that you can afford. But you can always, if you have a very slow simulator, sometimes you can only afford like 10 or 1, but sometimes you can also afford a different. The space of kind of inference problems that you can use in the setting with, for instance, nested sampling would be somewhere up here, right? So that's typically where nested sampling problem sits. If you have a cosmological problem, you can make 20 parameters. You can sometimes easily evaluate the trunk like this many times, so you can get an answer. That's fine. But the fun thing is, in some sense, that with neural simulation-based inference, you in principle could solve problems independently of the number of parameters. So there are caveats to this, but in principle, the kind of problem space that is addressable is now this here, everything above this right. And what does this mean? Well, in reality, often problems actually sit here. So if you analyze Fermi-Lat data, for instance, to really describe the data well, you certainly need to have thousands or millions of parameters because there are tons of uncertainty. So what's usually done is you try to pre-marginalize, you try to simplify your models, and somehow bring your model down to few enough parameters to actually use classical inference. That's not the only thing you can do, but it's practically done. And yeah, that part kind of disappears. With simulation-based inference, you can actually analyze principal models that are as complex as they need to be to actually. On the other. Just to justify this universal inference. So I think it's really useful to think about simulation-based inference not as yet another way of analyzing data, but kind of a way that all encompassing way. So there are lots of analysis techniques for image data astronomy. So Fermi-Lat, dark matter searches, things like template regression, line searches, one-point statistics, cross correlation. In some sense, you can think about simulation-based inference as like the thing that fills the gaps in between. Simulation-based inference is actually a way of deriving the most optimal analysis strategy for any given data analysis problem, rather than just an alternative. And it's useful to think about it like this, because one of the ways to test that you're on the right side of the track is to simplify your problem, see that you actually agree with your simulation-based inference techniques, traditional answers, and then kind of go the next step and look at the real proof. Good. So that sense it's universal. These are my conclusions. So there are lots of upcoming data, which also increases in quality. So that's one of the main headaches. So we have to make models more realistic, which requires less. Typically, thoughts means we can run less simulations, but have more parameters, which kind of is the opposite of what you need to run classical inference. Simulation-based inference can help. There's a lot of thinking that has to go into applying these techniques, but they are very powerful. Right, so with this, so if you want to play with this, you can start making some games, and it's very actively developed. Thanks a lot.
Thanks a lot, Christoph, for a nice talk. Is there any question in the audience? Yeah.
Thanks, Christoph. So, you had a slide on it earlier on, but I was wondering if you could touch on how this TN compares to, say, web-based methods like this.
Yeah, maybe I can show this. So the main difference between maybe so flow-based methods are typically used if you want to approximate the posterior or the likelihood, and for the rest of the video. So one problem when you want to approximate these function here is that they have to be normalized to 1. Otherwise, the algorithms don't. They rely on the thing that you optimize being normalized. And so flow-based models are essentially ways of defining neural networks such that using neural networks to define very flexible normalized distribution. That's not necessary if you do ratio estimation. The normalization kind of works off by hand. It's a result of the rather than something you have to quickly instruction. So what this means is that you can use pretty simple neural networks to do the ratio estimation. You can just use a trivial dense network and it will work pretty well. Whereas here you have to actually think about these rather sophisticated flow-based models. So in practice, what we found, I should say, what but this was also confirmed by others, is that this year is much easier to train. Also, found it much easier to train practice. At some point, I was sticking to that. That said, flow-based models have the advantage that they have like a bias in the sense that if you have a posterior that, so typically how flow-based models work is you start with the Gaussian, and then you apply all kinds of funny bijections to squeeze this Gaussian to the posterior you actually have. So there is like a preference in some sense for things that look like Gaussians. If your posterior is actually Gaussian or close to Gaussian, then this inductive bias, its preference for Gaussians, flow-based models can probably give you the correct answer with pure simulations. The price to pay might be that you have to give training. But in principle, there's nothing from stopping you from plugging a flow into ratio estimation.
Any other question on Zoom? Is there any question on Zoom?
Or they can speak up if they want to ask a question.
In the meantime, I have one, this part about lensing. And you said it will help on
Sorry.
the part of lensing at the end of the day. Will you be able to put a better bound on the mass of the dark matter? Let's say, for example, rule out the neutrinos or stuff like this.
It's a bit hard to say how well this will work. So I think it will necessarily almost certainly work better than traditional techniques, because with traditional techniques, so to speak, they're basically limited to individual halos. So you can only detect heavy halo, because otherwise you have too many degrees of freedom. So there are papers about the power spectrum approaches, but they are never, it's never been shown that this works in practice. So this year has the potential to actually work, and we thought, but we have to show it. So what we found is that in some sense, the network that is shown here actually figures out how to marginalize out the heavy halos that you don't care about, and still sensitive to the small ones, which is pretty good. So it should get better results than other methods in principle, but we have to see how good they are. But just to give a number, maybe down to 10%.